Okay, welcome everyone to the 88th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is J. Shah, and he'll be talking to us about real topological Hochschild homology, C2-stable trace theories, and Poincaré cyclic graphs.
Thanks for the invitation and the opportunity to speak. So the goal today is to explain certain extension of the formalism of stable cyclic graphs, which is a formalism meant to articulate various universal properties of THH, like the trace property, for instance, and THH as a universal trace theory. But now in the context of THR, real topological Hochschild homology, viewed as a functor of Poincaré infinity categories, C kappa. So what I want to try to explain today is a certain extension of the category of stable cyclic graphs, which you might label as lambda ST, to a C2 category. And in particular, the C2 category, which is a pre-sheaf on the orbit category of C2, will have C2 fixed points be a new notion of what I call Poincaré graphs, lambda P. So there's a C2 action on lambda ST, basically inherited from reversal of order. And this C2 action, if you can take the C2 hump to be fixed points, there's a natural way of extending that to an interesting category. And that's what I want to get at today. So let me maybe try to focus the discussion by stating two theorems about THH. Which this formalism of stable cyclic graphs is useful for. So theorem one is that, as I said, in passing, THH is the universal stable trace theory. So this category lambda ST, which I'll explain, is a natural domain for THH as a functor to spectra, and it's needed to articulate the universal property of THH in this way. As a very concrete application, you can use this to produce the following. So for every stable C and prime P, we have a cyclotomic Frobenius on THH that will make THH into a cyclotomic spectrum that we can, for instance, take the topological cyclic homology of. So this is very important for applications in trace theories, for instance. Theorem two, sort of in a somewhat different direction, is that you can make precise sense of the adage that THH is a linearization of algebraic K-theory, where here I mean, of course, in the sense of Goodwillie calculus. So implicitly here, I'm thinking of computing the tangent bundle of stable infinity categories. And this will turn out to be stable cyclic graphs on one vertex. Rather, it does turn out to be. This is, of course, not my result. It's a theorem. And along with this, you have to know the right adjoint to the cotangent complex in this setup, as identified with the functor that takes endomorphisms. So I want to try to at least explain the statements of the following Poincaré refinements of these two theorems, which I'll call pre-theorems. We haven't quite worked out all the details, but these are the results we're trying to obtain. So THR is the universal C2-stable trace theory. So this is meant in the C2 sense. I will have a C2 functor, THR, from this lambda P category to the C2 category of C2 spectra. As a C2 category is a pre-sheaf, that incorporates the restriction functor, as usual. And the key corollary of this will be that for every Poincaré, C kappa, again in a prime P, I have the real cyclotomic Frobenius on THR, now valued in the parameterized Tate construction. So I'm not going to explain this, but just think about this as being the analog of the Tate construction in this context, which allows you to endow the spectrum, the C2 spectrum THR, with a real cyclotomic structure and thereby take real topological cyclic homology of it. So this is needed, again, for the application to trace theories. And for instance, the Hermitian DGM theorem that Yonatan has explained if you look up a talk of his. Pre-theorem 2 is we have an analog of the tangent bundle calculation, but for Poincaré categories. And again, it turns out that these are essentially one vertex Poincaré graphs. And you can also identify the omega infinity functor with a certain Poincaré structure on endomorphisms. So I'll explain what that is. And with this calculation in hand, you can precisely say that THR, is the C2 linearization of real algebraic K-theory. And everything here is, again, in the sense of good Willy, but it has to be interpreted in a C2 parameterized sense. So I'm not going to explain proofs, can't possibly get there, but I'm going to try to at least explain the content of these statements, and in particular, what is this category of Poincaré cyclic graphs? And as part of that, I don't want to assume that people know about stable cyclic graphs to begin with, so I'm going to give a fairly lengthy introduction to stable cyclic graphs. So the first notion that you might see for THH, let's say R is a E1 ring, is a very explicit formula. Like maybe I'll take R tensor R over R tensor op, R viewed as RR bimodule to take this tensor product. Or maybe I'll use the cyclic bar construction, where here I'm taking A tensor B to A times B or B times A. But I want to explain THH as a functor of stable categories. For instance, this is useful for articulating universal properties as well as key abstract properties like localization sequences. So for THH of a stable category, you define by taking the trace of end objects in C as a dualizable object in presentable stable infinity categories. So here it's important that I maintain this distinction between small and large stable infinity categories. So that maybe it's a bit abstract. Concretely, this yields the following formula for THH, which should maybe be more well known. It's just the colimit. If I take the twisted arrow category and then project to C op cross C and take the mapping spectrum, then if you unwind what this definition is saying, it's just giving you this formula for THH as a colimit over the twisted arrow category. So twisted arrows are like f x to y, and then I send that to map y here. Now, this is all very nice, and it's enough, for instance, to get you an S1 action on THH, like you would get from viewing it as a cyclic object. But it's not enough to get you the cyclotomic structure. So to get cyclotomic structure, I want to bring in the stable cyclic graphs. Now, let me recall some basics about the cyclic category. So you have the paracyclic category, lambda infinity to begin with. This can be defined as a full subcategory of totally ordered Z-sets on objects which are isomorphic to 1 over nz. And let me label this as n lambda. So on this category, I have an S1 action. And on morphisms, so an S1 action is a Z action on morphisms. I have a free Z action, which sends to it with and it's translated by the integer. So then I can define the cyclic category to be the paracyclic category S1 homotopy orbits. And this is just the literal strict quotient by the S1, the Z action on the morphisms. So let's think of objects in the cyclic category as cyclic graphs. For instance, I might draw them like this. So Z, 1 over 1z, projects to the following cyclic graph. Maybe I want to draw the arrow in the other direction. Or I could have free vertices for 1 over free z, and so on and so forth. And this is really an honest description. I mean, I can think of these as directed cyclic graphs, and I then have a free category functor. From lambda to cat, which sends this n to what I'll call Tn, and that's just the free category generated by this directed cyclic graph. Now, so with these cyclic graphs, where does the notion of a stable cyclic graph come in? Well, I'm going to take this these vertices and edges and try labeling them. So I'll label cyclic graphs by stable infinity categories and profunctors, i.e. bimodules thereof. To just draw some pictures to explain this. So let's take the one vertex graph, and I have a stable infinity category C together with a profunctor F, and it's not important to understand why, but I have to label the arrows going the opposite direction. So the profunctor F is precisely just an exact functor from C to NC, or a functor in PRL, that is to say, colon preserving from NC to NC. This is the same as a bimodule, C cross C op to spectra. Or I could take two vertices, and then I would have F going from D to NC, and G going from C to ND as my profunctors. Again, the infinity categories in question are always small. So rigorously, the stable cyclic graphs on n vertices are objects of a category, cat x flat over Tn, of stable flat fibrations. over Tn. Here I use that exact correspondences are the same as profunctors. So this yields, of course, a description of the morphisms as lax squeezing squares. I'm not going to elaborate on that. And also a functor from lambda op to cat, sending n to this category of stable flat fibrations over Tn, where the functoriality is a pullback, so it's a contravariant functor. Now I can define the category of interest. So the category of stable cyclic graphs is the co-Cartesian unstraightening of this functor. So it contains all of the stable cyclic graphs, in particular as objects. And it possesses a structure map to lambda op in this case. Let's think of extending THH to lambda ST as taking generalized coefficients. So for instance, one vertex graph is just a bimodule. So I'm taking THH with coefficients in the bimodule. More generally, I have a multi-object setup. To explain a formula for THH, I, though, have to bring in some a few more additional objects. So first, I have the functor of endomorphisms from lambda st to categories. And this, in terms of these stable flat fibrations, is just taking sections. But again, it's good to draw some pictures. So let's look at this one vertex example with a stable category in the bimodule. Then the category of endomorphisms is just an object and together with a map alpha from that object X to Fx, and this is taken in C. Or I could, for instance, maybe not now say the general case, if I have n bimodules F1 through Fn, then I'm taking objects in each category, a CI in this case, and maps xi to fi xi plus 1, where these indices are taken mod n. Taken from, they wrap around to 1 if I take the n plus first index. Now let's let E be the composition of endomorphisms with the groupoid core. And a definition. So I want to somehow post-compose this to spectra with the infinite suspension, but then I want to stabilize to enforce some exactness. Precisely, I want to enforce the following. So given a functor, which we call theory from lambda st to spectra, I say that's stable if for all C1 through Cn, its restriction to this n-fold product of taking fixed vertices and any bimodules is exact separately in each variable. Then I'll let EST be the universal stable theory, the stable approximation to sigma infinity plus compose E. Concretely, I have a formula. So evaluated on some these n bimodules it's a colimit over what you can think of as the moduli space of the vertices, the categories that are labeling the vertices, and a tensor product over the mapping spectrum. Now, this is the functor of stable endomorphisms. So this is the thing that I want to regard THH as under, just like I phrased the universal property of K-theory under the groupoid core. I want to phrase the universal property of THH as under the functor of stable endomorphisms, THH coefficients. So let me first just give a definition in terms of a geometric realization. So THH of C, given this functor, can be taken as the following geometric realization. So for instance, these two face maps are, I take C, I label by identities, and I have two compositions which yield the same object. I can compose in one or the other order. And likewise for THH of an arbitrary object. Here I insert identities for in every place that I can. And I can compose either forwards or backwards consistently. So this defines, can make sense of this, and it defines the functor THH on the category lambda ST with a natural transformation from EST to THH. Now, what is the universal property in this case? Here's where we bring in the trace property. So we say that a theory has the trace property, if it sends co-Cartesian edges to equivalences. For instance, if I think about THH and what this is saying, let's look at a two-vertex graph. Then I can compose in one order, or I can compose in the other order. So in other words, THH of G compose F is THH of F compose G, which is what is reminiscent of a trace property. And this is encoded by this in this categorical setup by just saying it inverts the co-Cartesian edges, because these are the face maps, which are the co-Cartesian edges under the, this is for the functor, the functors in the image of the trace map. So they become co-Cartesian edges under the unstraining. So these are the ones that have to be inverted by to have the trace property. And again, then the theorem is that more precisely, THH is the universal stable trace theory under this functor here. And with this universal property, as I said, you can realize the cyclotomic trace map, and that's using the fact that I can also construct the target of the cyclotomic trace as a functor valued on lambda ST, which enjoys the trace property and is also stable, thereby obtaining a natural transformation. So that concludes my review of that very nice piece of mathematics. Now I want to get to something new. So Poincaré graphs and THR. So let's recall what is a Hermitian infinity category. Well, it consists of a pair, a stable infinity category C, and a functor, kappa, from C op to spectra, which is a quadratic functor in the sense of Goodwillie. And I say that this is Poincaré if the underlying bilinear pairing, B kappa, associated to the quadratic form, some people like to call this the cross effect, for instance, is representable by a duality. That is to say, a functor from C op to C, which is an equivalence. So in that case, BI is the mapping spectrum from X to dy. Excuse me. As an example, we can take C to be the category of perfect R modules, let's say over E1 ring. And then I can classify all Hermitian structures over C as modules over the HHR norm of R, viewed as modules, of course, in the symmetric monoidal category of genuine C2 spectrum. For instance, this is how E sigma algebra structures defining R yield Hermitian structures. In this case, they're actually Poincaré. Maybe more concretely, if R is E infinity, then you can look at a C2 E infinity structure, R underline, that is a C2 action on R and some choice of geometric fixed points, subject to some conditions. And a quadratic functor will be determined by the underlying duality, which is the R linear dual, plus the linear part, which is represented in this case by this geometric fixed points part. And then I glue them together using this map from geometric fixed points to the Tate construction, in this case. I guess I might have to also twist by the C2 action, but you can also suppose, for instance, that the C2 action on R in this case is trivial. Just to give an example. So to explain the idea of Poincaré graphs, it's similar to refining symmetric bilinear so kappa, so by symmetric bilinear kappa, I mean those quadratic functors which are completely determined by the bilinear part, by the symmetric, which is taken to be symmetric. So maybe I should explain that if I have B which is symmetric bilinear, then it specifies the so-called symmetric Poincaré structure. Here I'm taking the linear part to be basically the Tate construction associated to the bilinear part. So there's no necessity of specifying the linear part specifically. You can also think of this in terms of the recolement on quadratic functors if you want. So it's sort of an elaboration of this idea of passing from symmetric bilinear to general quadratic. But yeah, to explain that, let me first explain some C2 actions I have on lambda and lambda st. So I have a C2 action on lambda by reversing the order of the directed cyclic graph. In terms of the paracyclic category, this would be from a Z semi-direct C2 action. So Z semi-direct C2 sets with this order, where the C2 action reverses the order. I also have a C2 action on stable cyclic graphs as the categorical dual. So this is in PRL ST. Remember, I already had introduced this in the context of describing THH as the trace of a dualizable object. But here, I'm invoking the idea in maybe a related way. In terms of my pictures of a stable cyclic graph, let's consider, for instance, this. Pre-vertex stable cyclic graph. Then the C2 action trades this for something where I dualize first the vertices. So here I'm using that if I take in C dual, in the sense of the categorical dual, that's equivalent to in C op. So I can replace the vertices by the opposite categories. And if I have some colimit preserving functor from in C to in D, say F, or maybe I'll say F, here it's from D to C. I'll say F bar to indicate the extension. Then dualizing will yield something I'll just call F check. And that goes in the other order. In terms of the bimodule, if you try to write this as, for instance, in this case, D cross C op to spectra, then you can use the symmetry on the domain to define this duality. In terms of the stable flat vibrations, you just take the op of some stable flat vibration over Tn. Now, this functor from lambda op to cat, which defined lambda st, this intertwines the C2 actions. So this structure map from lambda st to lambda op is C2 equivariant. First of all, lambda st inherits a C2 action, and its structure map to lambda op is C2 equivariant. Let's now consider the fixed points. So this has also a structure map to the fixed point category of lambda op. in lambda op, what is an object? It's some, let me just label it by the category generated by the directed graph. It's some Tn together with an chosen isomorphism between Tn and its opposite or reverse graph. I'll draw these as follows. So if I have some vertices, then it's choosing an axis of reflection. So I can have axes of reflection that fix vertices. I could fix a vertex under this isomorphism, or I could, for instance, not fix one and just have orbits which are all free under the C2 action. Then in lambda st HC2, let me, for instance, look at the picture over a one vertex graph where that vertex is fixed. The op action sends this to C check or C op, excuse me, and F check. But then I reverse. So how to say it? And that transports this graph with the direction of the arrow flipped back to graph where the arrow goes in the preferred order. And then my equivalence, my fixed point datum. So this transportation is used. You use the fixed point data of the base, that those pictures in lambda op HC2 I drew up upstairs. Then the fixed point datum in the total category identifies this F check and C op with the original graph. So I have a duality, in other words, identifying C and C op, which should make you think I'm going to get to Poincaré categories soon. And these profunctors, the profunctor is equivalent to its dual. This means that if I use the duality to write down a bilinear form, by linear pairing, so let me label this as F, then BF is symmetric also. So let me also draw another picture. So you can also have something where I have a fixed point free graph. And then being a fixed point of the category means I took the ops and exchanged and reflected about the axis. And then I have F check and G check here. So D is equivalent to C op. And with respect to this duality, F is equivalent to F check and G is equivalent to G check. So I have bilinear, these symmetric bilinear functors. So from lambda st homotopy C2 fixed points to get to the actual category of Poincaré graphs, I want to consider quadratic refinements of this data. Just like how I refine a duality to an actual, a general quadratic functor. So I'll just say that this is done as follows. Given first a fixed vertex and an equivalence between then the category labeling that vertex and its opposite, you promote to a Poincaré category as a label, and given an identification of some bimodule with its dual, you promote this to a hermitian structure. In other words, let's call this kappa F, and this will be the coefficients for THR. So if I want to draw a Poincaré graph, here are some examples. I have C now with a Poincaré structure, and I have labeling the edge a hermitian structure. So I prefer to draw this, or rather write this hermitian structure as being on C versus kappa, which is from C op to spectra. But of course, C is equivalent to C op, so this distinction is not a distinction. Maybe the more general case in this situation is actually the fixed point free situation. So in this case, let's call these, I'll label the bottom one as C and the top one as C op. The axis of reflection is, again, I'm drawing that horizontally. Then the edges are labeled by two Hermitian structures, kappa F and kappa G, where kappa F is on C and kappa G is on C op. This covers the underlying stable cyclic graph, where I have the associated, not duality, but profunctor. Maybe I shouldn't call that D, but it's, let me just call it F. So from the bilinear pairing, I, of course, have the bimodule itself. And likewise on the right-hand side. And this is actually as I was saying, in lambda STHC2. So there's a fixed point datum there as well. So, of course, I haven't told you about the maps, but that will be getting a bit too technical for this talk. Vaguely speaking, these pictures assemble into infinity category lambda p, such that I have a C2 category which is, again, a presheaf on the orbit category of C2, together with C2 co-Cartesian fibration over lambda op HC2. Where the C2 category, which is the base, is just the Borel extension of the C2 action of lambda op with its C2 action. And in this case, C2 co-Cartesian fibration is simply a fiberwise one. So before, I had this composite. I took endomorphisms. I took the core. And I took suspension. And I took the stabilization or linearization. To get my functor of stable endomorphisms, which then I define THH as being under. Now, I have this category of Poincaré graphs. And let me draw it together with the entire as a C2 category. Refining this end on the bottom, which is C2 equivariant, I have some notion. So there'll be some functor to cat P. For the core, as is well known, the correct C2 refinement, if I think of cat P as this is stable category. If I think of cat P as a C2 category, then I should take Poincaré categories. Which will end I should take Poincaré objects as a C2 space. That's basically I have a Poincaré category. Its C2 moduli space of objects is just given by this. Then I have sigma infinity as before. The thing to note is that end in this situation requires a Poincaré structure. And that's easy enough to explain what that is. If I have some C kappa and kappa F, and let's say that covers F composed D. So this is how I'll write it. Let me write kappa F as really being, in this case, from C op to spectra, just to make the formula cleaner. So then F is from C op to in C, which corresponds to the bilinear pairing determined by F. So end consists of X and C, and some alpha, but this is just BF of X dx. And I can define kappa end on this X pair X alpha as kappa F of X, kappa X, and a pullback square involving them. Where this is the vertical arrow here is the canonical one. The one below is as follows. So I can go from kappa X to this mapping spectrum because it just passes through BXX. It's the underlying duality or bilinear pairing again. And then to define this map here, that sends morphism F to the pullback of alpha by that morphism, where alpha is my chosen element of BF dx, BF x dx. So I'm not expecting you maybe to absorb the formula, but the point is that one can write down a very concrete formula which promotes endomorphisms for the underlying graph of this Poincaré graph with one vertex, in this case, to a Poincaré category. And now, to conclude, let me bring the discussion back to this notion of tangent bundle that we saw earlier. Actually, let me first conclude the discussion about THR. So you can define using tools from parameterized category theory. Obvious, well, I should say maybe natural extensions of everything above. in particular, the notion of C2-stable trace theory, which admits so the notion of stable trace theory admits sort of an obvious parameterized generalization. Then you can exhibit THR as a functor, as a C2 functor on this category, and as the universal C2-stable trace theory under what turned out to be, again, some C2 parameterized extension of the functor endomorphisms. And the application I'm principally interested in is, again, to get the real cyclotomic structure on THR of some Poincaré capital. Now, let's return to the tangent bundle formalism. So I had stated that we have a computation of the tangent bundle of stable categories as being these one object stable cyclic graphs. So in other words, I just have a stable category together with a bimodule. This is something you expect, for instance, if I take literally perfect R modules over an associative ring, and I take then bimodules. Moreover, if I take omega infinity in this case, which would be, it's a generalization of taking the square zero extension of a ring by a module, then this is exactly that endomorphism functor I wrote down earlier, restricted to the cyclic graphs with one vertex. So this connects then the picture of Goodwillie calculus, where I can view, so the way in which I have a functor and I want to compute its linearization is to restrict it to the tangent bundle and then take the linearization there. From this point, you can see that THH restricted to this lambda ST1 as defined earlier computes the linearization of algebraic K theory. In the Poincaré setting, the key computation is as follows. You actually can compute the tangent bundle together with its structure map to Poincaré categories as being given by Poincaré graphs on one vertex, where that is, again, the fixed vertex, and there's only one possible way to fix it, together with this functor of endomorphisms in the way I wrote above. So I just pulled out the formula for you, but that formula is actually canonical in view of this computation of the tangent bundle of Cat P. And from this, you can again get that THR restricted to lambda P1 is, now I have to phrase the universal property, I have to say it's a linearization. This is a linearization in the C2 sense of real K theorem. And again, this is as a C2 functor. So I think there were a few more things I wanted to discuss, but this is actually a good stopping point. So I'll pause and ask for questions now.
Thank you, Jay. Let us all unmute ourselves, and give the speaker a round of applause now. Okay, there are a few. Yeah, quite a few people are clapping virtually. Right. If you have any questions for the speaker, you can ask them now. So, Jens, yeah.
Yeah, I mean, so that's very nice. What does it tell you about the trace? Does it tell you anything new about either its construction or properties or?
So I think that it's the right way. So if you think about how should I say it? Even the construction of the cyclotomic structure. So in THH, I'm not sure if this maybe answers the question about the trace specifically, but to construct the receptacle of the trace, namely real. Oh, sorry. Are you talking about the trace, the cyclotomic trace, or just the trace map from K theory to THH? Because that the map from K theory to THH is produced by this this Goodwillie formalism. So
no, the lift to the cyclotomic structure.
okay, right. So that I think the right way to conceptualize the construction of the cyclotomic trace, first to construct the cyclotomic structure on THH is to view it through the lens of this formalism of stable cyclic graphs. Because that handles so there's the cyclic subdivision, right, step in understanding let's say the CP action on THH of C is basically using the trace property. And that's organized correctly by this formalism. So it's the right way to get TC as an invariant of stable categories, at least. And then for the trace map, remember, sorry, I think I'm don't want to say something wrong, but I remember the story being a bit tricky, actually. But I was focusing here on the yeah, I think you want to get the trace map somehow separately, just using the universe property of K theory. So you can do that independently of this formalism.
Okay, so that is really somehow a different story. I see.
Yeah. So I mean, you invoke the universe property of K theory. I guess you want to establish things like localization sequences for that, but you don't need that for you don't need the formalism of stable cyclic graphs for that. Maybe to prove it for TC.
Yeah.
Sorry, I think that they're separate stories.
Yeah.
For the my purposes, I just want a clean construction of the real cyclotomic trace. The real cyclotomic structure, which is necessary, of course, to define the receptacle of the real cyclotomic trace.
Yeah. And are these very nice structural results you just presented, are they supposed to help also in computations in some example, or rather not?
So I don't believe that they per se are useful for calculations. I mean, so the concrete way of maybe interpreting this is that it produces various different formulas for THR or THH for that matter. So I brought out like two different formulas, for instance. One is this colimit over the twisted arrow category, and that has an analog also in the C2 setting, and also by the cyclic bar construction. And you have that they agree. But yeah, I don't believe that it's necessarily useful for computations.
Thanks a lot.
Oh yeah, so for Gabe's question, absolutely. So this is the right way of getting the real polygonic structure on THR with coefficients. But I haven't again done any calculations on that. I mean, for that, it's very important that we have somehow all of the graphs in play. Yes, I don't know more. I'll just leave it at that. It's some of the vague statement.
Thank you. Any more questions? Let's see. Okay, if we don't have any more questions, let us thank Jay one more time. Okay, thank you all for coming. We have Matt Booth from Lancaster University next week.